This is the second tutorial that I plan to do using FreeCAD and CalculiX. In this case, we're doing a thermal analysis and also a thermomechanical analysis, which will mix together the results of the temperature analysis and the strains that are induced due to temperature changes and how these affect the mechanical behavior of a very simple component. I'll go through this as a series of steps. First of all, I'll present some background and also some theory and general information. So again, I'd like to try and connect what's going on in this tutorial, in this exercise, with the theory that I've been presenting in the previous videos on different lectures. In particular, it's connecting the theory presented on heat analysis in the video for lecture 5. I'll then use FreeCAD to build a model. I won't be using CAD options. I'll use something different this time, so it'll be slightly different to the first video. Then we'll go on to mesh the model and then define thermal boundary conditions, materials, possibly other loading, etc. And then I'll be doing 3 main types of analysis. First of all, I'd like to show you just standard thermal analysis, and then we'll do a transient thermal analysis, and then finally I'll move on and do the thermomechanical analysis, where we consider both linear and nonlinear material behavior. First of all, this gives some brief information on coupling thermal and mechanical analyses. If you look at the top relationship here, the strains in the material are equal to the compliance matrix times the stresses that are acting, plus any strains that are imposed due to thermal effects. So this would give us our total strains. I've just given the compliance matrix here for a 2D material. We're assuming here that the material behavior is isotropic. Also, in these thermal strains, you should note that it's only the X, Y, or the principal strains that create volume change. Shear thermal strains don't create any volume change, so they have no meaning and no contribution to these total strains. So in abbreviated form, we've got this equation here. The thermal strains are the temperature change that's been imposed or applied, multiplied by the thermal expansion coefficient for the material. So I've done all this here for an isotropic material. You can have anisotropic materials with different thermal expansions in different directions, in which case you would have a temperature change, and then you would be using different expansion coefficients in each of the principal material directions. But the basic idea stays the same. If we invert this, invert's probably the wrong word, let's reorganize it. We bring this over this side, then we can get the stresses in the material, and that would be given by this relationship here. So the stresses imposed will be the strains the material is undergoing minus the thermal strains, which are given by these, all multiplied by the elasticity matrix for the material. So E is the inverse of the compliance. Stiffness is the inverse of the compliance. And in full matrix form for a 2D isotropic material, we'd have these relationships. Now, in a practical analysis, usually the way it's done is you do 2 steps. First of all, you do a thermal analysis to get the temperature distribution. And from this, you can compute these thermal strains. These thermal strains are converted to stresses here. So we multiply the strains by the modulus. And these stresses multiplied by or computed using this relationship are converted into nodal forces. In other words, these are the nodal forces that would give us the strains, the thermal strains that the material is experiencing. These nodal forces, internal forces, are then added to, in a second analysis, are then added to any external applied loading. And then we use our normal relationship here for a mechanical analysis. So we invert the K matrix, bring it over this side. We can then get our displacements. And from our displacements, we can get the element displacements, and then we can get the element strains and the stresses. So it's a two-step process. First of all, a thermal analysis, results being fed through, temperature results being fed through to a second mechanical analysis. This is a summary of the key matrices for heat transfer analysis. These have all been derived in the video on lecture 5, but I just wanted to review the equations here. If you're not so interested in these, you could jump over it, but it's just to give you a chance to look at what the key matrices are. First of all, maybe I'll start here. This is the conduction matrix. So this is computed for all elements in the problem. It's integrated over volume for a 3D element. It would be over area multiplied by thickness for 2D and so on. These are our standard B matrices that we derived for different elements in the video on lecture 2. And this is our conductivity matrix for the material. So in a mechanical problem, this was the elasticity matrix. In a heat transfer problem, it is the conductivity matrix, which is basically this here. This would be Kx and Ky. If we're dealing with anisotropic or orthotropic materials, this would be K1 and K2 in the principal material directions, and then you'd have to do a transformation to get this conductivity matrix in a Cartesian frame or the element frame. If you're doing this transformation, it becomes fully populated. If it's an isotropic material, you would have Kx equal to Ky equal to K, conductivity. So this is done, as I say, for all elements, and the usual assembly processes are done for the elements to give you the capital K stiffness for the structure. If we have surface convection, then we have this matrix which is computed over all of these surface elements where convection is applied. There will also be this vector where this is the environmental temperature, and this is the heat transfer coefficient for the surface. So this will only be done for the elements that are, this will only be done for the elements which are on the surface where this convection occurs, and this will be done on the surface elements or the faces or the surface faces of the elements. If we have an imposed flux, some flows being imposed at the surface somewhere, then this would be the equation that would be used, and here is the value of the flux. This will basically convert this flux to equivalent nodal values, which will be in here. If we have internal heat generation at some particular point, then this vector will be computed for all of the elements where this heat generation is occurring. So this could be, for example, some heating element internally. And essentially this whole operation here is converting the internal heat generation amount to equivalent nodal values, which are put in here. If we have a transient problem, we now have to take into account the capacitance of the material and the density. And this will be done for all of the elements in the domain. The whole domain, you would have to do this, and they will be assembled in the usual way. Again, this is converting this sort of quantity to nodal values. So all of these will be added together for an element, and for the complete structure after assembly you would have large R values here. These will be assembled here. K plus KH, so this of course will be for all elements. This will be only for elements on the surface. This is the nodal temperature, and this capacitance matrix, again, this would be for the whole structure, and this is the rate of change of temperature. So this makes it a time-dependent problem. So I hope that gives some idea of the assembly. Just to make one point clear, these only apply, or there are only values in here for the certain nodes where these particular heating elements occur. However, the total vector, this total vector will be the same size as the total temperature vector for the structure. It will contain very many zeros. Any zeros on the surface for a node on the surface would mean that there would be no flow of heat across the surface. If you like, it's perfectly insulated. Any zeros for an internal node of the structure is basically enforcing continuity. It's saying that the flow going into the node and exiting the node is balanced. This is really quite the same as what we did in mechanical analysis. There are many zeros in the load vector, and that is enforcing that you have a balance of internal forces at the nodes. One of the analyses I will be doing will be a transient analysis, which predicts how temperature changes with time as heat flows through a component. In this case, the set of equations governing the problem is given here. These are our flow equations. This is our standard conduction and nodal temperature equations. And this is the capacitance and the time-dependent temperature. And this is the part that's making giving a time dependence to the solution. Now, I did in the lecture on lecture 3, chapter 3, I did go through solution methods, but I rather jumped over direct integration and the Newmark method. And that's what's used here for analysis of this time-dependent temperature problem. So I will give a very quick explanation of what's going on for this solution. The idea is that we want to try and find temperature, nodal temperature, from known information at time t to predict what's happening at t plus delta t. So we've got a forward time step here. We can assume this kind of a relationship where we say, okay, the temperatures at time t plus delta t is equal to our known temperatures plus some factor times temperature rates at time t, plus beta and temperature rates at time t plus delta t. So for example, if beta was 0.5, you would have this one plus this one divided by 2 multiplied by the time interval. So it's given us a forward prediction of time. This would be reasonable as long as, of course, the behavior between this time and this time is linear. So we can use this idea with this equation to come up with relations at time t and time t plus delta t. So expressing this at time t gives us this here, and expressing this equation 1 at time t plus delta t gives us these terms. And all that's being done here is a small trick where the first equation is multiplied by 1 minus beta and the second equation is multiplied by beta. It's just a mathematical trick to simplify things. But if you do that and then you add these two equations together and use the fact that this is equal to this minus this divided by delta t, if you simplify all of that, you end up with this expression. We've got rid of our rate terms, and we see here that the temperature at t plus delta t is equal to all of this, which contains known information at time t, with the exception of this term here, which is the flows. We have to assume we know what the flows will be, the surface flows at times t plus delta t. Of course, this assumes things are linear. In other words, these conductivity matrices, capacitance matrix and conductivity matrix, are not changing during this time interval. If they are, then you will have to do this within some kind of an iterative scheme. So this allows us to find updated nodal temperatures. It's so-called conditionally stable if this beta is greater than or equal to 1/2. That means we can use, theoretically, we can use any time step and the solution should be stable. If beta is less than 1/2, then you have to use an explicit integration scheme, and you have to use a certain time step, which is given by a certain criteria, which I've given in the book, but I haven't stated it here. But normally we would use an implicit scheme with beta equal to 1/2. So that's basically the idea, and it's what, as I say, that's what's used in CalculiX. Or this basic idea is used within CalculiX. I mentioned at the beginning that a thermomechanical analysis, first of all, you do a thermal analysis, you determine temperature distribution, and these temperatures are fed through to a second analysis, which is a mechanical analysis, which converts these temperatures into strains, thermal strains, which are then converted in effect to nodal forces, added to any additional applied forces, and the mechanical analysis is performed. Now, I will be showing you how we do that with CalculiX, but in fact, by default, FreeCAD will write out the thermomechanical analysis in such a way as to activate a certain option which is called coupled temperature displacement. And this does one analysis of those previous two I just mentioned, in which a Newton-Raphson iterative technique is used to update displacements and update temperatures so that you have a solution that matches the applied thermal loading and mechanical loading. So it's all done within one step. If you haven't got any mechanical boundary conditions or mechanical loads, it will also do a standard thermal analysis, but it will use this iterative scheme. I've listed a few points here regarding this particular analysis. As I say here, it's coupled, thermal and mechanical within one step. A step is basically one analysis. So you have a starting step, if you like, and an end step. You could have another analysis after this, in which case you would have a step, a load of information, and then an end step. And information from this analysis would be fed through into the second analysis, and so on. There is one of the tutorials I do has 3 analysis steps, in the book that is. In this step you list information like boundary conditions, thermal loading, output information, it is, as I say, an iterative scheme based on Newton-Raphson. It does require initial temperatures to be set. This is a bit unusual. If you do a standard thermal analysis, you don't need to specify any initial temperatures. The solution will find the temperatures. But for this iterative scheme, you do need to set initial temperatures. They can be any kind of value, and it will hopefully converge to the solution. Because it's coupled temperature and displacement, it is usually advisable, and I do usually constrain it in some way. So you need some mechanical boundary conditions. It can do steady state or a transient dynamic analysis. So for example, just specifying this keyword without anything here would do a transient analysis of the type I've just shown you on the previous slide. If you put in here comma steady state, it will do a steady state analysis, in which case it will ignore any capacitance matrix and time-dependent effects. It can also handle large displacements. You would have to put in here geometric nonlinear. And it can also handle material nonlinearity. For this, you would simply have to define a plasticity curve, for example, for your steel material, and then it would do a nonlinear material analysis on Mises, for example. An alternative to this is to do as I mentioned, and I will show you how this works. We can duplicate this. So you copy that whole block and you put it down here, cut and paste. For the first analysis here, you would put heat transfer, comma, steady state. And then for this analysis step, it would do a simple thermal analysis. And then this information will go through into the next step. And in that next step, you would have here static, just simply static, which means it would do a simple mechanical analysis. And you would find you will get essentially exactly the same results. In the second mechanical analysis, you could include large displacements, material nonlinearity. The problem of doing that, I will do it, but the problem of doing it is that FreeCAD cannot post-process the results. You have to use the special graphics processor from CalculiX, and I will be showing this. So as I say, I will show an example on how this works when we come to the analyses. Now the problem I've selected is a very simple plate. It's 10 millimeters thick, 100 millimeters long, and 50 millimeters wide, with a central hole of 25 millimeters. Now this example is based on another YouTube video that's available on the web. I've listed it down here. It really is a very good tutorial, and I would suggest you have a look at that, but look at it after the one I do. I think it's the better order, because you will understand this one a little bit better perhaps. And what's particularly good with this tutorial is that he shows some very nice post-processing. He doesn't do material nonlinearity. I will touch on that, so you can have a look at this one and maybe do it and modify. But the dimensions of the part he's analyzing, I'm using here. Okay. Some information that we'll need for the analysis. In particular, it's the heat conduction coefficient, so how heat is emitted from the surfaces, or how heat is transferred perhaps from the material here to some, could be a liquid running through this hole. This could be part of a very large plate in these directions. If you are using gas in a free convection, this is typical heat transfer coefficients, and the default value in FreeCAD is 10, so I will use the default. If we are assuming, for example, water flowing through tubes, it's somewhere between 500 and 1200 heat transfer coefficient. I will use a value of about 700 or 800. So that's just to support some of the data we'll be using. But what I'll do in a moment when I start FreeCAD is I will build this model, mesh it, and do a few different analyses. They will be slightly different, or they will be different to the ones done here. But then I do suggest you have a look at this one. It is quite nice and shows very nice post-processing options that I don't show. So I've started FreeCAD. I'm using version 19.3. We'll create a new file to include this plate with a whole structure component. Now I could create this in different ways. I could, for example, go into the Sketcher workbench, rather like I did in the first tutorial, and create the outline of the plate, add a hole or add a circle that could be extended or extruded into the block. I could do a similar thing with the draft workbench. This draft workbench is really for doing 2D type structures, but again, that could be you could create the circle and the rectangle and merge these to give you, with an extrusion, to give you the plate with a hole as well. But I'm going to use the part workbench here. I'll start off by adding, well, I should say the normal way to do this, I think, is to create a part container, and then everything within this container relating to this plate and this hole would be added. The idea then is, if you have a set of different parts, you can manipulate those and add them together. But for this very simple structure, I don't tend to use this particular container. I just go ahead and make the part. I'll do this with, first of all, using a cube. Here we can see the cube created. If I then click on this, I can change the dimensions down here. So I'm going to give it 100 by 50 wide, and default it's already 10 millimeters thick. So if I move out, reposition this, you can see I've got the outer dimensions of the plate itself. I'm going to reposition this so that the centroid is here actually at the moment, or the origin is here. I'd like to move it so it's in the center of the plate. I can do this using the position option. I'll move backwards -50 in the X direction and -25 in the Y direction, so that's fine. The reason is, when I add the cylinder now, the cylinder is positioned at the centroid here, so it's automatically in the center of the rectangle, of the solid. Again, clicking on that, I can change the, come down here, I can change the radius to be 12.5. The height is 10, so this is giving me the basic outline that I need. Now I have to remove the cylinder from the cube. I can click on both of these, and I can use a Boolean operation to do this. Now there's a whole range of operations possible here to split parts, merge parts and combine them. I need the Boolean exclusive OR operation here, and simply by clicking on that I will remove the cylinder from the hole, or from the plate. We'll now go about meshing this. I start up the FEM workbench. I'll add a container. The solver is already added there, as we will need that later. Now, if I click on here, I'll open the two possible meshes. Gmesh doesn't work very well. At least it produces a nice uniform mesh, but I have no possibility in this version to create a local refinement around here. There are options using this icon here, this tool here, but unfortunately it's not working in this particular version as far as I can see. So I'm going to use the NetGen editor, mesher. Click on there. We'll try first of all using the very fine option and see what it brings. Okay, it's a reasonable mesh, but obviously too coarse for what we want to be doing here. So I'll go into the user defined. I'll specify 3 for the maximum element size. I'll use a growth rate. We'll try the 0.3. So this is specifying how the element sizes can change from one element to the next element. They can increase by 30%. Around the radius, or around the curved hole, we would like to have a finer mesh. So I'm going to put in, let's put in 6 there for 6 elements per radian. Click apply, see what that brings us. It's really not a bad mesh. There are some poor elements. I can see 1 or 2, and of course I can't tell what's inside. We could try a slightly different scheme. Maybe I'll use a different growth rate. Click apply. This looks a little better, and in fact it's really not bad. I'll move it around. Well, no, there are still 1 or 2 not very good elements, but I think I'll use that. I think you get the idea. You have to play around with these parameters to try and get something that looks suitable for the analysis you want to undertake. But I'll use this. We'll say OK. And now we have to go about setting up the problem for a thermal analysis. Now the first analysis I'm going to do, I'm going to apply 200 degrees here. I'm going to work in Celsius rather than Kelvin, just to make life easier for me. So I'm going to put 200 here. I'll assume around these surfaces we have simple convection to atmosphere. Atmosphere I'll put at 23 degrees Celsius. And I'll assume this is part of a long structure. So this is a slice, if you like. So I won't define anything for this surface and the rear face. That means there will be no flow normal to these directions. If I define nothing, it is a natural boundary condition which will have 0 flow. I'll assume that water's running through this tube. Perhaps this is a long part of a tube. Water's going through there. I'll use a different heat transfer coefficient here, and water may be at 40 degrees. And we'll do a simple thermal analysis to start off. So I'll switch off the mesh, click on that with the left mouse key. With the right mouse key, I can hide selection. And up here for the geometry, our show selection. So we can define the different parts now. First of all, I've got to define an initial temperature. This is necessary for this iterative scheme that I mentioned a little earlier. I'm going to set 23 degrees. Do keep in mind, although it's saying Kelvin here, I'm going to be using Celsius. It makes no difference to the consistent units. We'll say OK. So the whole thing has a initial temperature for this iterative scheme. I'll rotate round so I can see things a little bit better there. I'll define an initial temperature with this icon. I have to click on there and add for the face. And the initial temperature here, I'm going to specify 200 degrees Celsius. Okay. For the other three faces, we'll have to rotate to see them. We'll use this icon here. I'm going to add this one. You can click on these with the control key and you can get several at the same time. Rotate around, okay, I can just see it there. Click on that and add. So I've got the three faces. We're going to use this standard 10 watts per meter squared Kelvin. Do remember here that we have these units in FreeCAD. This is the default set of units for FreeCAD. But when we write out the data set to CalculiX, it will use different unit systems. It will be in millimeter Newton seconds. There will be a conversion made. So, but just stick to whatever you see here for specifying the quantities. So we're going to stick to this 10. And we're going to put the ambient temperature at 23 degrees. We say OK. Bring this structure back. We're going to do the same thing for the center where the liquid is running through. I have to click on this and say OK or add. We're going to specify here 800. These are numbers that I showed in the table earlier. And I'm going to say the water temperature moving through there is 40 degrees. Okay. So we've got initial temperature. We've specified 200 degrees here. We've got convection to air here. And convection to this water flowing through here. We need to define a material. I'm going to use CalculiX steel. Again, sticking to the units here, there will be a conversion made. Here we see the density, which will be necessary when we do a transient analysis. This has no meaning for the first thermal analysis. Mechanical properties, they will be necessary when we do a coupled thermomechanical analysis. And here we have properties for the specific heat when we do the transient analysis. Conductivity for how the heat flows through the material and the expansion coefficient. So this is okay. It is advisable to impose a boundary condition, mechanical boundary condition, when using this coupled mechanical thermal analysis option in FreeCAD and CalculiX. So I'm going to fix one face at least. We can do that with this option here. Add, and that means that face at least is fully fixed. So for the first thermal analysis, we're going to fully fix that. I say OK. Now ideally, I don't tend to do that here. It takes a bit of time, but you should give all these really a sensible name. This becomes very important when you do a large model. So for example, you'd click on that. With the right mouse key, you could do a rename and give it a sensible name like fixed face or something, but I'll avoid doing that at the moment. So really, we can do an analysis of this now. I double click on this solver, activate Thermomechanical. I'm going to write out the input file, but I will also save these results to a directory that I've set up, because I'd like to maybe to look at these results in a moment. Write the input file, and I'm going to edit it just to look at what's in there. Now I've activated a certain tab in the solver, which uses splitting of the data set so that we have include files for information like the elements and the nodes, for the constraints. And basically I'm left with just the core information that I really want to look at a little bit more closely. The analysis is done in this step here, between step and end step. So that's the main part of the analysis. Here we have the information on the type of analysis that's being undertaken, and it's using this iterative scheme, which does a Newton-Raphson type iterative solution for the displacements and the temperatures. For this we had to give these initial conditions for the scheme to get started. In this particular case, we've specified here that it's doing a steady state analysis. So it will ignore density and the capacitance of the material, and it will just solve the thermal heat analysis problem. We have for example here, these are the boundary temperatures which we set for 200 degrees. These are outputs. Okay, they haven't really, it's not necessary for me to make any changes here at the moment. I'm just going to save this and we'll run the analysis. And this may take a little time, so I'm just going to stop the video for a moment. So the analysis finished after nearly 30 seconds. I'll close this window here. I'm also going to switch off or close these constraints, hide selection. And I'm going to look at the results files here. And temperature is the only one that interests us at the moment. And you can see here the maximum is 200 degrees, reducing to 83 degrees. So here is our heated end. It reduces down to 83 degrees. There will be heat lost from the surfaces, plus of course considerable heat lost to this for this liquid moving through this hole here. I'll close this. We could use the pipe option to produce better plots, contour plots, but basically you'll see the same sort of thing. I'm going to delete this data set here and that file, and I'm going to do another analysis. We'll start the solver again. I'm going to save the results to this particular directory. Thermomechanical, write the input file. Now I'm going to edit it, and down here I'm going to use, instead of this iterative scheme, I'm going to use heat transfer. Now this will undertake an absolutely standard thermal analysis. It will compute the characteristic matrix for all of the elements for conduction. It will compute the characteristic matrices for the elements around the outside and around the hole for the convection. And you'll have a right-hand side containing the vector of convection surface heat transfers. It will invert the total characteristic matrix and compute the temperatures. We're going to do a steady state. So this is at the end, if you like. There's not going to be any transient effects taking place. In this particular case, we do not need this initial condition information. So I'm going to delete it. We also wouldn't need the mechanical fixing that I did, which I think is in this file here, but I'll leave it because it makes no difference. You'll also see there's no density here because we're not doing a transient analysis. So I'll run this now. We'll save it and we'll run that analysis. First of all, you will see that it will go much quicker. So it's taken 4 seconds instead of, what was that, 30 seconds before. And it's finished without error. We'll close there and we can have a look at the results. And you'll see the problem is that it says basically it can't reload those results. This is a problem. We can do the analyses, but we can't look at the results using FreeCAD. So as an alternative, you have to look at those results using the CalculiX post-processor. Now, if you've installed that, and I mentioned how to install it in the lecture on lecture 7, it's the B converged for the Windows installation at least. If you've done that and you double click on this results file, it's the .frd file, it's the one that's just been created. We double click on that, we will see the results of this standard thermal analysis now. For example, you go into dataset and here entity temperature, and then you will see we get exactly the same results, 200 degrees at this heated end coming down to 83 degrees at the remote end. I'm going to close this up. And what I'll show now is a transient analysis. So we close this. Now you can change the analysis type in here. I don't tend to like working with this so much. For example, well, some of the things you can do here, for example, this is this split option for splitting up the data set. And if you wanted the complete data set, you'd put false. And if you want to have these include files and split it up, which is a useful thing to do, I think, you have true. If you say true here, it will do a thermomechanical steady state analysis. If you put false, it will do a transient analysis. So I'll leave it at false. This is the starting time for the analysis, and this is the end time. Now I'm going to edit that in at the data in the data set. I must admit I prefer not to be changing these things too much, but sometimes it's an advantage to do that. But I'll edit this in the data set when we run this. I think that's the only change we need to make at the moment. I will start the solver. I want to save the results to this particular file. Thermomechanical analysis, write input file, and then we'll edit the input file. Now down here, we will see density now appear. This belongs to the still material that we defined at the start. It wasn't in the thermal analysis. Now it is here, because if we're doing a transient analysis, we will need this density together with the specific heat value here. We need this initial temperatures. It again appears. I deleted it, but every time you rerun or restart and rewrite the data set, then of course all the options you defined in FreeCAD will appear here. And what we've got now is a coupled temperature displacement analysis. If you remember, we had steady state here before. Now that's not appearing because we're doing a transient analysis. If I put direct, that would be the key word for doing a transient analysis, but by default it is activated. And here this is the start time and this is the end time. Now I'm going to analyze just for 100 seconds. So we're going to see how the heat, what this means is that the whole plate will have this initial temperature. This 200 degrees at one end is going to be applied, and we're going to see how that heat moves through the structure with time. Everything else remains the same. We'll save these changes and we'll run the analysis. Now this will take time, so I'll stop the video. So this transient analysis has finished successfully. We can see no error at the bottom here. I will close this panel and we can now see some results. So this is our starting time, this is our end time. First of all, we'll just look at the end time, temperature. And we can see we've got our 200 degrees here, but this end has only increased from 23 degrees initial temperature to 30 degrees. It's only raised by 5 degrees. We can close here. If I look at, for example, 75 seconds, we've got 200 degrees at this end and 23.4 degrees at this end. So hardly any temperature increase at all. There are some better plotting options using the Graphix-CGX post-processor. I'll quickly show those. If we go in and open this this file, this is our results file. We can, for example, look at an animation of this. You have to do animate, toggle data sequence, and then you have to specify the first or where you want to start the animations from. We're doing temperature. You can see other contour plots are possible there. You've got displacement, stress, and so on. And then you come in again and have to specify what you want. So this is the temperature. And then you can see how the temperature is flowing through the structure. You can see the 200 degrees, obviously at this end, 23 degrees down here. So at this point, it's hardly increasing in temperature. There's another useful option. You can come in here. I hope you noticed that. I'm clicking just outside the box here in order to open these panels. Then you do graph, for example, time. Let me just move this across because it hides another useful panel. There's information here that you have to look at, but for example, I will click several nodes. So that's 1, 2, 3, 4, 5. I'm clicking on those with the left mouse key, and with the right mouse key you finish that operation, and then it will produce this plot of those points from the starting time to the end time, so 100 seconds. There is a line along here which is right at the very beginning of this component, so that's at our 200 degrees. And then the next node I selected is increasing. Well, 23 degrees would be down here, but it's increasing up to just over 160 degrees. It's reached within the 100 seconds. Nodes at the very end have only increased to just over, what, here 30 in this case. And obviously it would take a long time looking at this in order to reach a steady state heating of that particular problem. These curves are saved in the directory. If you come in here and you look down, you will see these curves created. Let's go back into FreeCAD. I'm going to move on now and do a thermomechanical analysis. So we're going to introduce some more sensible constraints on this structure. I'm going to put close. We'll leave everything else the same. I will delete these results. I'm going to delete this constraint that we had. And what I'll do is I'll fix this end and fix the other end. It'll be heated up by this particular heating and cooling. And it will, due to this heating, you will have thermal strains created. Those thermal strains will be converted to stresses, and those stresses to nodal forces. And those nodal forces will be will create deformations of this particular structure. So let's fix this. First of all, we need to constrain one node. In order to have no rigid body motions in these directions. So I say OK. And then in this one, I'm going to select this face and I'm going to rotate around to collect this face as well. And I'm going to fix those only in the X direction. They can expand freely in that direction and in this direction. That's fixed. Okay. Now we'll use this standard coupled thermomechanical analysis that's in FreeCAD CalculiX. First of all, let's well, one thing we have to do is to switch off the transient analysis. We want to just do a steady state analysis. So we'll do a steady state analysis to get the temperatures, and they will be used to compute these thermal strains. Let's save these results also in this directory that I set up. We'll write we've got thermomechanical here. We'll write this out just to have a look. We haven't got any density occurring here now because it's a steady state analysis. You could also argue we don't need this information either, but it would be ignored. We've got this coupled temperature displacement and we've got steady state here. These values have no meaning now because it's steady state. So that should be fine. I'll save this here and we'll run CalculiX. Now this may take time as well, so I will just stop the analysis or stop the video. So the analysis took just under a minute. We'll close this panel and we'll look at some of the results. These results are wrong. There is a mistake somewhere. Whenever you see this NaN, it means not a number. It means really some rubbish has been generated, and the whole thing here looks wrong actually. I think the problem is that I haven't specified enough boundary conditions. At least that's the first thing I'm going to try. The constraints for X, Y, and Z are properly defined. The whole structure cannot rotate this way because of the constraints imposed here, but it can rotate this way around the X-axis because I haven't got a constraint here. Strictly speaking, you have to suppress 5 rigid body modes. So I'm going to delete all of these results. It's very dangerous to try and open those. Trying to plot things that are not a number is dangerous. I'm going to add another constraint. So I will come in here, I'll click on this particular line and add that, and I will say that that cannot move in the Z direction. That will suppress rigid body rotation around the X-axis. We'll say OK, and we'll rerun the analysis. Again, I'll save it to the directory as before. We write the input file. I'll run the analysis this time. I don't need to go into the editor. And I'll stop the analysis because it does take a little time. So that took just over 30 seconds. We close here. And this time we only have one results file. It's much more promising. Double click on that. Temperature. We can see the temperature has gone from 200 degrees to 83 at this end. Let's have a look at the deformations. Displacement magnitude. And we can maybe exaggerate things here. And we can see now the structure is expanding. It's the sort of deformation we would expect. Seems reasonable. These are the magnitude of the deformation. If we look at von Mises stress, we've got stresses minimum 18 megapascals going up to 745 megapascals. Now this is well over typical yield stress for steel, so this is unlikely to happen. We should really think about using an elastic plastic curve and doing a nonlinear analysis, and I'll show you this in a moment. I'm going to close there, and I'm going to redo this problem in a slightly different way. We'll activate the solver. I'm going to set my directory as usual. I'm going to write out the input file. This time I'm going to edit it. So we are doing got it here, a coupled temperature displacement steady state. Now, if you remember at the very beginning, I said the normal way we do a thermomechanical analysis is we do a thermal analysis, compute the temperature distribution, and then these temperatures are used in a second mechanical analysis where the temperatures are converted into strains, stresses, and nodal forces and used within the mechanical analysis. Now I'm going to do that here. I'm going to take all of this information down to end step. I'm going to copy it into the buffer, and then down here I will add it again. For the first analysis up here, I'm going to put heat transfer. And for the second analysis, I'm going to put static. Now, if we wanted to do an elasto-plastic analysis, we could add that information further up here, just below the elastic. I could put in plastic, star plastic, and then the hardening curve for the material. And when it comes to the second analysis, the static analysis, it will automatically do a Newton-Raphson analysis to work out the elastic plastic stresses. I think maybe we'll do that, but I'll well, let's do that now. I'll have to get the information for that curve. I have to go back. Have to go up one. Okay, what I have just done is to get the information for this plastic curve, which I had saved in a directory in a file. I'm going to paste it in here. Okay, so what this analysis should now do is a standard heat transfer analysis, steady state, to get the temperature distributions. The temperature distributions will go into the next analysis, which is a static analysis. This has no meaning. I can cut that away. And because we've now defined a plasticity curve, this analysis will also be a nonlinear Newton-Raphson analysis based on that plasticity curve. There is in this step you will have some temperature information, and in this step you may have some mechanical information. In each case, what's not needed will simply be ignored. So I'm going to save this, and we'll run the analysis. Now this too may take a little time, so I'm going to switch off the video for a moment. So the analysis took 39 seconds. It finished without error. But as you can see here at the very bottom, it failed to load those results. That's because FreeCAD now doesn't understand the results that have been created from this CalculiX analysis. So I have to, in this case again, go into the directory and look at the results file using the CalculiX post-processor. And what you will see now are two sets of results under data sets. First of all, this will be the temperature analysis results. So we can look at that. You click on that, then you have to come in again under entity temperature. And here's our temperature analysis results. Again, we see this 200 degrees down to 83 degrees. It's a static analysis. Then we go into the second analysis, mechanical analysis. We see lots more information. We could look at stresses, displacements. Let's look at displacements first. You have to do that again, going through to entity. We'll look at all displacements. And there's our displacements. And these should be the same as the previous analysis I had done in FreeCAD. Let's look at the elasto-plastic stresses, and hopefully now we should see stresses that follow the elastic plastic curve we defined. So I select stress. Again, I come in, and down here we'll have von Mises. And it looks promising. You can, if you look back to that elastic plastic curve I defined, the yield stress was at 400 megapascals, and it hardened with strain up to about 400, and I think it was 450. And what we can see here is elastic plastic stress of 424 megapascals for von Mises. And you can see here the zone basically that is plastified. Now you could do that exactly the same analysis using the FreeCAD coupled thermomechanical analysis with this coupled temperature option, and you would have to just define the plasticity curve, and it would produce the same sort of results. So that basically covers everything I wanted to go through. I hope that hasn't left you too confused. It has tried to show you how you can do separate thermal and mechanical analysis, and sometimes it will produce the results within FreeCAD, and sometimes you have to look at these results via the CalculiX post-processor. I would suggest, if you're interested, to run the other video I had mentioned, YouTube video from Michael Hinckley, just before I started all these analyses in the slides. It's quite a nice video. He shows some very useful information on defining boundary conditions. He also shows some very nice information on how to do post-processing using Python scripts. Now, if you don't want to do that, you can use the CalculiX post-processor, the CGX post-processor, to also get the information. But I hope you did find that useful. It covers basically everything I wanted to.